pleasure to be here. I think all of you would know me. I've been around long enough, not as long as Professor Dennis McLaughlin, but long enough, about 20 years. It's great to have this. It's great to have the opportunity to tell you, a little bit quickly, in an hour, some of the things that have been going on in my research group over the years. So that's a partial list of people contributing to various aspects of what I will be presenting. So this is a bit of a bestiarium of things that have happened, and some of them quite some time ago, others more recently. So I like to start with this slide. This talk is about flowing porous media, and the flow can be flow of miscible fluids. So you have one homogeneous fluid where the composition might change, or you can have immiscible flow where you have a flow of two immiscible fluids, in which case you have surface tension playing on. So this is a gravity current experiment. You have a lock exchange, you have a light fluid on the left and a heavier fluid on the right, and then you just set this in motion. And if you have water and glycerol, for instance, these two fluids mix in all proportions. So the water runs up, the glycerol slumps down. But you see sort of this very smooth pseudo interface between the two fluids. Now you repeat the experiment with the two fluids that are immiscible. They don't mix at all. And you have an interface, an actual interface in between. And this, of course, taking place in a porous medium pack of glass beads. So the air in this case runs up and the water slumps down. But a good fraction of the interface, of the initial interface, doesn't move either way. And this paper is from 2013, which means that the experiment was probably done in 2011. Right? So some of these cells are still in my lab, and it still looks like this. So this interface will never move. So why? So you can. So this illustrates a little bit like the way we work. So we do some experiment that we don't understand, and then we try to visualize with some analog experiments to see what is going on behind the scenes. So for that, we can use a microfluidic chip. So you have pillars essentially that are round. Everything is very ordered, and you can image perfectly the interface and so on. So when air is displacing water, this is drainage. In this case, it's even, we use silicone oil for this experiment just to remove any ambiguity about contact angle or so. Air is perfectly non-wetting, and silicone oil is perfectly wetting. There's no hysteresis. So for air to move, it has to squeeze through the pores, so it has to adopt configuration with a small radius of curvature. So there's a pressure associated with that small radius of curvature. Whereas for silicone oil to invade, to displace the air, it doesn't have to squeeze through anything. It has to hug the poles. So that configuration has a much larger radius of curvature. So these two pressures of invasion, air displacing silicone oil or silicone oil displacing air, without any hysteresis in contact angle or anything, just by virtue of the fact that you have a porous medium, you have a disordered medium, those two pressures are different, and they have to be taken up by gravity. So delta rho g h is equal to that difference in pressure. So that's what explains the fact that that interface doesn't move. And the message here is sort of more generally that immiscible flows are a different beast from immiscible flows. So even in this very simple configuration, you can see that happening. So whenever you have two phases and you have a substrate, there's an additional property that comes into play, which is the wettability of the medium of substrate with respect to each of the two fluid phases. Also, we talk about wettability, which is a measure of that solid substrate affinity to one of the fluids. So we say, look at this countertop is wetting to water, the water spreads, but the lotus leaf is non-wetting. The water beats up. And this presentation really is all about some, illustrations of how wettability is important. I will go through a number of examples or a number of illustrators. Starting with very simple systems, like spreading of a liquid on a flat surface. You would agree with me that that's very simple. But then getting into adding more complexity to the problem. So we have confinement in the form of a capillary tube or a microfluidic chip, and then a porous medium. And then at the very end, I'm going to go through the slides quickly. I would like to get to the last section because some of you might not have seen that, including Dennis here. So I would like to reserve some time for the interaction between fluids and the porous medium skeleton itself. Okay, so we want to describe the spreading of a liquid bottle on a flat surface, smooth surface. But we want to do that not in 3 dimensions, but rather by tracking the height of the film, right? So it's a vertically integrated model. So you can cook up or write down the free energy of the system, no? And you have the ingredients that you might expect. So gravity and then surface tension and then interfacial tensions between the substrate and each of the fluids. So that's the macroscopic component. But when you have interfaces that are close to each other, there's an additional component. They start to feel each other, right? Something called disjoining pressure, which is essentially a reflection of the fact that you have excess energy because the 2 interfaces are close to each other. And the theoretical arguments and atomistic simulations actually indicate that that excess energy is also dependent not only on how close the interfaces are, but whether there's an angle between them. So we account for that. You can make some mathematical approximations that are not so relevant so that you end up with a more familiar type or more familiar form of the free energy. But basically it has a macroscopic component that depends only on the thickness of the film. And then it has what is known as an interfacial component that depends on gradients of that interface or film thickness. Sorry. You can impose some constraints. The variation of the free energy is 0 at equilibrium, and you require continuity between wet and dry states to constrain what these functionals, what the form of those functions has to be. The end result is that you end up with an equation just to be solved for the film thickness, just an equation that reflects or embodies the fact that you have partial wetting. So if you look at the bulk or macroscopic component of the free energy, instead of being just a parabola, which is what you would expect for a completely wetting system, you have a bulk free energy that has sort of a double model. You can draw the Maxwell tangent construction and determine what is the ultimate film thickness, which is going to depend on the contact angle of the liquid with the substance. So this is, again, just to say that completely wetting systems would predict, or a formulation that is applicable to completely wetting systems would predict that the puddle continues to spread indefinitely. If you account for partial wetting, it does not. And the model then makes other predictions, like the rate of spreading is different. This is without any further tuning or anything. The rate of spreading of the puddle is different if you have a large puddle or a small puddle, because the driving forces are different, right? So these different power laws for the rate of spreading reflect that automatically. And then microscopically, you might be familiar with this idea of dynamic contact angle. So you have an interface that advances along a substrate, and depending on how quickly it advances, the contact angle is different from the static contact angle. So usually in models, you put that in as a parameterization. Here you don't have to do that. Okay? So the model, the balance between viscous and interfacial forces, it predicts that the advancing contact angle is going to be dependent on the velocity of spreading, and therefore it will decrease with time. And so the puddle spreads more quickly initially and then more slowly later on, and that advancing contact angle changes as dynamically as a result. Okay, so that's sort of the simplest example, a puddle spreading on a flat, smooth surface. We can think about another very simple configuration, but slightly more complicated in the sense that we now have a confined fluid. So this is just a capillary tube, and you displace one fluid that is filling the tube initially with another. And you would think that, in the 21st century, we would have figured out that problem already. And no, I think many aspects of it have been figured out, but surprises remain. In our case, we were interested in determining sort of this transition from a meniscus advancing coherently at slow speeds to what happens at large speeds, where the contact line cannot keep up with the front of the meniscus. It just isn't able to keep up. And as a result, the system starts to leave film of fluid adhered to the walls, the inner walls of the capillary tube, and eventually that leads to pinch off of that slug of the invading fluid. So experimentally, we were interested in determining when that transition occurs as a function of wettability, and I think conceptually no surprises there. If you have a hydrophilic tube, you're going to start leaving a film of the wetting fluid early, at lower speeds than if you have a hydrophobic tube. No, you can develop a very relatively simple, just mathematical model, hydrodynamic model of the shape of the interface, and that agrees very nicely with what is observed experimentally in terms of when the wetting transition, when you start when you go from a meniscus that advances to leaving this so-called Brotherton films as a function of wettability. But we're interested in what happens beyond that wetting transition. I'm gonna show 3 videos simultaneously. And like when you see the newspaper, what are the differences? Right? So you have to see what are the differences and what are the features that are the same, that are common to all 3. Right? So these are 3 experiments that are identical except for the injection rate increasing, being larger at the bottom than at the top. So there are many things that are different. Okay? I'll play this again. Like the meniscus advances at different speed. But what is the same?
It breaks, no? Where it breaks, is it the same location?
Well, so this is not necessarily the end of the tube, but the end of the window that we're capturing with the camera. But what is the same? Again, what is the same is the speed of the contact line. It is independent of how fast we inject. So this is something that we can take advantage of, because essentially it is telling us that after a little while, we can decouple what happens at the contact line from the motion of the meniscus. So we can build a model for the thin film itself, independently of what happens to the meniscus. So this type of model, I'm not going to get into, but it's sort of the same kind that we built for the puddle that was spreading on a smooth surface. It has some additional features because you have an additional curvature here, right? That you didn't have on the flat surface. But the model predicts quantitatively this feature of this mound of fluid increasing over time, and then universally leading to pinch off of the slug of invading fluid that form. And that agrees quantitatively with the experiments. As a side project, one of my students at the time, Amir Polavan, took interest in really understanding the pinch-off phenomenon. That is actually a fascinating thing. So it turns out that it is universal. You can collapse all the behavior of how that pinch-off occurs into a single master curve of neck radius with time. But how that happens is what is really interesting. This process of pinch-off undergoes two regimes that mathematicians call self-similarity of the first kind and self-similarity of the second kind. So the self-similarity of the second kind is the one that remembers history. So it would lead to a non-universal pinch-off process. But because that is preceded by a regime of self-similarity of the first kind, that's the kind that forgets the history and is independent of the initial conditions, all the history is forgotten by the time you get to the second regime. Anyway, I'll just show you a picture, a high-speed video of the pinch-off, just as, and again, he developed, so this was, Dennis knows him very well, Amir, who likes these kinds of fluid mechanics problems. Okay, so more recently, we've done some work on trying to model model this type of processes mathematically, and then implement that in a computational scheme. And you would think that this is, there should be, again, no mysteries here. You just use the Navier-Stokes equations with something like the Cahn-Hilliard equation to account for the interfacial effect, and then away you go. But you have to pay special attention on how to model the boundary conditions. The contact line is a complicated beast, and there are different ways of tackling the motion of contact lines computationally. In the type of models that we've pursued, which are called phase field models, diffuse interface models. Let's see if I can explain this in very simple terms. You have to transition from the wetting energy of the solid substrate with one fluid to the wetting energy of the solid substrate with the other fluid as the contact line passes by. So how do you do that? Well, in the past, people would have used some interpolation scheme, really just a straight line or a cubic or a spline or something, or a hyperbolic tangent to interpolate between two surface energies. But that turns out is grossly incorrect. So the interfacial energy, the interpolation scheme that you have to use is tightly tied to what the bulk free energies are. And otherwise, unless you account for that inner structure, unless you respect the inner structure of the diffuse interface, so you see these functions here, you don't get the right even static contact angle. Okay, so that was, and this is just very, very recent. So there's still some surprises to be found in the lost and found section. Okay, so this model agrees nicely both in terms of the static contact angle and dynamic contact angle and the morphology of the interface with the experiments. By the way, in this section of the presentation, the flow, we reverse the images and the flow is from right to left. I'm not gonna get into why that's the case, but aren't you curious why that's the case? So that was the lesser of the two evils, because in addition to the numerical model, there was a mathematical model of that is classic. It's a classic model of the motion of a wedge that has an analytical solution. But that wedge, it was defined, and all the expressions and what everybody in the field uses was defined with the angle this way. So we had to let this angle become the angle in the meniscus, so that the flow had to go from right to left. So we spent a great deal of time, many meetings, deciding which one of the two we were going to do, and this is the way we came in. Okay, so the experiments, even when you go to, this is why I was saying, no, Kepler 2, we should have figured it all out by now, but if you have a very smooth to borosilicate glass of very high quality, you do these experiments now from right to left. At low flow rate, you have this meniscus, and then at high flow rate, these are perfectly wetting conditions, perfectly wetting. So the fluid that we inject is silicone oil, and it's perfectly wetting. And if we inject at a high enough speed, the meniscus reverses and then eventually starts leaving a film. So this is what the experiments show. And that is also, this is not a video, but just a still image. That is also what the model predicts. But a few years ago, a good friend of mine, Denis Barthelot, his group, did some experiments, not exactly in a Kepler 2, but in a microfluidic channel, where they did this type of experiments, and they observed, and they are good experimenters. So we borrowed actually a lot of their techniques in our experiments. They saw that there was now the fluid is going from right to left, and at low flow rate, you have sort of this compact-like displacement in the thickness dimension. But then at some point, you undergo this wetting transition, but in a very different way. So by by forming a pilot film of the wetting fluid ahead of the meniscus, completely incompatible, like diagonally opposite to the behavior that we had observed and that our model predicts. This is a PRL paper, you cannot just ignore it, right? And this is a good group of experimentalists. So which one is it? Right? So we did our best to repeat these experiments, our experiments, under their conditions. So the main difference, key difference really, was that they were using a polymer in their experiments that we've also used, you'll see in a moment, No81, that has the capability of modulating the wetting properties. That's why it is used, but it is rough. And you can see, you look in the microscope, and it has roughness to it. So we coated our tubes with the same polymer, with No81, and repeated the experiments. So at low speeds, you see the meniscus advancing, and there's a kind of a jagged motion actually that is detectable. But then at high speeds, before you get into the regime of meniscus reversal, you start to see this pilot film advancing. Okay? So the lesson here is that roughness of the substrate fundamentally alters the way in which inhibition occurs. Okay? So we were, well, I would say in a way relieved that we got to understand where the difference was coming from. Okay, so this, we're transitioning now to more porous media-like applications. And the way in which we've done that in the past in our group is by using microfluidics. Microfluidics is a very, many of you know and use, it's a very powerful technique because you have very precise control over the geometry. It is really sub-micron precision. And you can visualize that. So there's some trade-offs, there's some limitations. It's not three-dimensional. It's not like a rock, right? But it allows you, gives you a lot of flexibility to zoom in and understand what's happening. So we did some experiments of viscous fingering in disorder system. So it's a circular microfluidic chip. We inject at the center with a low viscosity fluid to displace a more viscous liquid. Okay. So that has been done many times. What has not been done many times is to explore the entire range of contact angles. So here you see a kind of a visual phase diagram where we can control the injection rate. So at the bottom is low injection rate, at the top is high injection rate. And then from left to right, we go from what we call drainage to imbibition. So the fluid that we inject is less wetting on the left, and it is more wetting, is very wetting actually on the right. And this was, we arrived or we accomplished the ability to reach all these conditions by using this polymer No81, which if you subject to high energy UV radiation, it becomes hydrophilic. So you see different patterns. No, this I guess the title of the talk was inspired a little bit by this visual phase diagram. Some of it is well understood. So you go from invasion percolation or capillary fingering to viscous fingering on the drain under drainage conditions. You also see different colors. No, and I always joke that this is not so it is cosmetic, but it is not for cosmetic reasons that you see different colors. So there's a color bar that tells you what the color indicates. It is the fraction of the thickness that is filled with the invading fluid. So if you see very bright colors, the entire thickness is filled with the fluid that you inject. If you see warmish, orange, red color, means that only a fraction of the thickness is filled with invading fluid. So this is also reflecting leaving these Brotherton films at the earth to the top and bottom. Anyway, so there are some trends here that you observe, but then something happens at a given contact angle, and you start observing entirely different patterns and entirely. So that was, I guess, the main finding from this experimental exercise, that the microscopic or pore scale mode of invasion changes entirely when you go across this transition from weak imbibition to strong imbibition. And because we're using microfluidics, we can zoom in and we can get all the details. So we zoom in part of the cell, and what you see is that the invading fluid is not squeezing through anything. It is coating the pillars and then joining to another pillar nearby and advancing that way. Okay? And that is particularly noticeable at low injection rates. This is a movie that has been sped up, I don't know how many times, but this process happens, but it happens in sort of avalanches. The films form, and then they have to swell enough to reach to a neighboring pillar, and then there's a cascade of coating events. So this is like we were hypothesizing. This is like what the physicists call invasion percolation, which is very well understood for pore invasion, but it's like the strong imbibition counterpart of invasion percolation. You're joining pillars or nodes through these links that the films are forming. We later on, many years later on, we decided to quantitatively look at the data set, and indeed, the data set shows that this invasion percolation like phenomenon shares all the features of self-organized criticality phenomenon that is well known and well understood for drainage. Okay, so as we move towards more realistic porous medium, we are not the first ones to observe that drainage and imbibition behave differently. This is one of my favorite papers. It's by people at ExxonMobil at the time. Second author, I guess, is Dave Waits, who has been now for several decades a very famous professor at Harvard. And so they have a series of papers where they illustrate this, very nicely, that drainage viscous fingering in a porous medium is very different from imbibition viscous fingering. So when the invading fluid is more wetting than the defending fluid. So we decided to take a closer look or a more comprehensive investigation of this phenomenon. And you see here, once again, this type of visual phase diagram with the same axis as before. So the capillary number is a reflection of how fast you inject at the center of the cell. Now this is a Healy Shaw cell, a cell filled with glass beads rather than microfluidic fillers. And here we traverse from drainage conditions to weak imbibition conditions. And we expect in drainage to see viscous fingering at high speeds and capillary fingering at low speeds. But what we see is a compactification of this pattern to an extreme. So at low injection rates, even though the fluid that we inject is, in this case, I think 500 times less viscous than the defending fluid, it displaces the defending fluid completely, right? So there's no fingering whatsoever, and wettability is solely responsible for that compactification. Of course, you can think of reasons why this could be practical or important in practice. And what I would like to do for the remainder of the presentation, or what remains in this bestiarium, has more to do with the interaction between the fluids and the skeleton, the grains, or the skeleton of the porous medium. So we were originally, back in the day, interested in this problem to better understand venting of methane in lake sediments. Right, so if you have an organic rich sediment, the conditions are usually such that there are the right type of bugs that will produce methane, and that methane will form bubbles, and the bubbles may link up and then be expelled to the water column. So we were interested in that problem, but that problem is, of course, sort of more general, of having one fluid displacing another, and perhaps modifying the pore space as it does. So one can think of, really with a back of the envelope argument, you can think of forces that act in the direction of dislodging the contacts between grains, and forces that act in the direction of keeping those contacts in place. And so pressure, either capillary pressure or viscous pressure drop, may act to dislodge the contact. And if you have cohesion or cementation or friction, those will act to keep the contacts in place. So you can define a couple of dimensionless numbers that capture the balance of forces, and then do a bunch of experiments. By the way, you must have realized by now that all of our experiments are on circular cells. So there's also a reason for that. There are some disadvantages, clearly, right? So you inject at a constant rate, and you have a compact displacement. The velocity of the front decreases with time. The balance of forces changes with time. That's not ideal. Yet we continue to do experiments with a circular cell. There must be a reason. And the reason is that they are, like, many times, as in 2 orders of magnitude more reproducible than experiments in linear cells, where the boundaries really are going to affect the flow in so many different ways. And it's very, to us, in our experience, very, very difficult to reproduce, say, spatially homogeneous injections at one end of the cell. So that's why, that's the behind the scenes explanation of why you see so many circles in my presentation. Okay, so you do experiments where you vary different parameters so that you vary the balance between capillary and viscous forces. So this is well understood for rigid medium, and we've seen it already. You undergo a transition from capillary fingering to viscous fingering. That transition is smooth. So the fractal dimension changes gradually. But then you can change other parameters like the weight that you exert on top of the cell, or the grain size, or the viscosity of the fluid and the injection rate. And you undergo a different transition that is much sharper from pore filling to conduit opening. Now we call that hydrocapillary fracturing, not hydraulic fracturing, because at high rates, at high injection rates, this is like a hydrofrac. You're blasting fluid in, and the pressure doesn't dissipate, and you just open fractures. You dislodge contacts between the grains. But this happens at vanishing injection rates too. Right? So the problem is different, but think of a desiccation crack. A crack forms at vanishingly small rates. So the physical chemical mechanisms are different, but I think of that transition sort of as an analog for how you can go from capillary fingering to capillary fracture. And us being interested in wettability, now we say, well, let's repeat this experiment, but with different wetting conditions. So in drainage, you see this regime in which it's mostly viscous fingering, this wispy viscous fingering-like pattern, but you see kind of a combination within the same experiment, a transition to fracture opening. There's some faint fractures that are forming towards the end of the experiment, and that is because as the pressure builds up, the effective friction decreases, and you're able to open these conduits. And now we repeat this experiment. Everything is the same, other than the fluid that we inject is now more wetting. Everything else is the same. So very different invasion morphology. Right? So if you are, I'm going to extrapolate here in a cheeky way. So if you're an operator and you want to maximize fracturing, right? Because you want to then, I don't know, deliver something into the medium or extract something from the medium, and you have a low porosity medium. There could be something here that you want to take advantage of. And then you say, well, let's take this to extreme. We go to the strong imbibition regime. The fluid that we inject is super wetting, so we're going to get just even more fraction in the sense of maybe like just 2 or 3 fractures developing only. But instead, we don't see any fracturing at all. So we now understand this as having gone through that wetting transition, the fluid that we inject, instead of squeezing through the pores, it is now coating the grains and not providing the pore scale pressure support to dislodge the grain contacts. Right? So wettability plays a role. I think that this illustrates, even when it comes to the interaction with the porous medium itself. There's couple more things I want to talk about. One is related to what I've discussed now, but the driving force is now gravity. So this is a problem that hydrologists are interested in. So you have precipitation over soil, and then that water is going to permeate downwards into the soil. And you go to the field and you observe immediately some of these patterns of columnar infiltration patterns, where you don't see any obvious heterogeneity or any obvious channel that is responsible for channelizing that water that is infiltrating, right? But you do see it. So clearly, this is in a desert sand after a storm. The wind blows the sand, but because of the remaining cohesion from the infiltration, there's some patterns that reflect where the water went and where it didn't go. Right? And this is literally a kitchen sink, quite literally a kitchen sink experiment. So this is an ant farm cell, so just glass beads packed in a quasi two-dimensional cell, and then just water dripping from the top. It was actually me dripping this water, maybe the one and only experiment I've ever conducted in my life. So I was not trying to squeeze like a little bit more water at every pass at the same locations, right? So I wasn't trying to do that. And this is a perfectly homogeneous sandpack. Yet the infiltration is very heterogeneous. And you have these columns forming. So this is kind of undeniable. If you have a coarse sand or a sandpack, and you have this type of infiltration, this is what you would expect. This is very different. And if you introduce layering, for instance, you say, oh, well, I'm going to kill this instability. Not so. So locally, and we understand this well because of the capillary forces are different, there's a swelling, or the width of these fingers increases in low probability layers, but these fingers then just continue across the layers as if they never saw them. And there's a model for infiltration in soil. It's called Richard's equation. That doesn't have this instability in it. No? So the analog that I like to use is imagine that we describe fluid mechanics with the Navier-Stokes equations, but the Navier-Stokes equations were incapable of reproducing turbulence. Well, that would be a problem, right? But this is the situation that we are in. We use an equation that cannot reproduce this phenomenon that I would say is a very powerful and very obvious and universal phenomenon. So you can go through the motion of writing down the interface of the system and recognizing that there's a non-local component to that free energy, and then you introduce mass conservation, you derive the chemical potential from the variational derivative of free energy, and you arrive at an equation that is like Richard's equation with an additional term. This additional term doesn't have a free parameter. That parameter is tied to the balance between capillary properties to capillary to gravity balance. And then it accumulates with this equation. And then indeed, of course, you get the fingering that you expect. And you can understand under what conditions that fingering is very vigorous versus the conditions under which it is not. And maybe Richard's equation is perfectly applicable. So this, in my estimation, could have some implications, right? Because if you're interested in recharge, for instance, the first few centimeters or maybe tens of centimeters of the soil are going to be subject to evaporation. But if water can infiltrate past those 10, 20 centimeters, then it is free to go. So if you can do that through this instability, you would predict recharge in areas where that are fairly dry, where Richard's equation would never predict that the waterfront would advance sufficiently and lead to recharge. And this has very robust field observations behind it. So we see active recharge in areas that are very dry and endowed with a very thick, homogeneous soils or porous media. Okay, and the last thing that I want to say in just a couple of minutes is a recent development. Every time I give this talk, it's less recent than the time before, but we're actively working on it. So I think that the term recent still qualifies because we are actively working on it, which has to do with something we call photoporomechanics. So when we are interested in this interaction between pore fluid and the skeleton of the porous medium, especially if you think of a granular material, the idea is to use photoelasticity. Photoelasticity has been used very successfully as a technique to interrogate the stress of a solid. Right? So the principle is birefringency, and in effect, what it does is that when you subject a birefringent material to polarized light, that the brightness and the color of that light that you observe depends on the stress that you apply, not the strain, the stress. And to make that point clear, I wrote down the equation, right? So the retardation factor is an integral of the deviatoric stress in the plane perpendicular to the polarized light. Okay, so photoelasticity has been used, as I said, very fruitfully, including or even maybe even especially to better understand phenomena related to behavior of granular materials. But until now, it's all been done in 2D with disks. So that's fine. But if you're interested in the interaction with the pore fluid, it's not fine. Because wherever you have a contact of two disks, the fluid cannot go through. So you cannot have a connected pore space in this type of configuration. So instead, what you need is a three-dimensional granular material where the pore space is connected. So this is all work led by a former postdoc in my group, faculty at Stony Brook, Wei Li. So he developed the technique to fabricate these beads. The important thing is that the beads have to be small enough, and they cannot be centimeter size, and they have to be residual stress free. Otherwise, the photoelastic response is completely polluted by the initial internal stresses, right? So these are he's devised a squeeze casting method to produce these residual stress-free beads, which can be spheres or can be other shapes. This is, I will show this. Is this video running? Let me see. Just so that you see. So this is Wei squeezing these beads. You get a feel for what that looks like, and they're polarized light. Here they're in a capsule filled with fluid. I think he's going to squeeze that capsule and then release it. And as it releases, there's some air that entrains. And there's a clump. And then those stresses, which are now from the clump that has formed as a result of capillary cohesion, they still remain in the clump. Anyway, I don't want to completely run out of time. So what governs deformation and failure in granular materials, in porous media, is not stress, it's effective stress. So this is a concept put forward by Carl Terzaghi, and I think he postulated this when he was at MIT. He spent several years at MIT. His office, I think, was on the third floor of Building 1, very, very close to where my office is. And that was more than 100 years ago, and it was a conceptual construct. He said the effective stress is what is effectively deforming the medium, and is the total stress minus what is transmitted, the part of the stress that is transmitted to the fluid, which is the pore pressure. So that remained very useful, as I think you all know, very useful concept that had never been visualized, tested experimentally. So this is the first visualization of effective stress. So this is a cell where you have a granular pack filled with fluid. You load this granular pack with a load that allows for the fluid to leak out, but not the beads. And as you do so, you exert increasing stress between or throughout the granular pack. And as a result, that brightness from photoelasticity builds up. Incidentally, in Terzaghis consolidation, the ultimate state is one in which you have uniform effective stress, which you don't see here. Why? Well, because in Terzaghis consolidation, you have a laterally extended medium. So it's a column, something that is extended in the horizontal direction. This is confined between two walls. So the walls are sustaining some of that load through friction. Okay, so the deeper you go, the more part of the load that is sustained by the wall friction. So you end up with non-uniform effective stress with depth. So the idea with this, I will finish, is to take this to truly 3D systems. In principle, these photoelastic beads would allow for that to happen. One of the technical complications is that, of course, spheres will induce a strong refraction of light, but you can take care of that by immersing the granular pack in an index match fluid. So the index of refraction is matched, and as a result, you don't see that refraction of light as a result of the curvature of the beads. And then you develop a tomography technique for the body that you want to image, right? So this rests on this idea that you have a penetrating wave that from which you can obtain a projection. You rotate that sample, so you obtain many 2D projections, and then you reconstruct the 3D object. So that is the principle that we use here. Here is it's the photoelastic response that you expect, not that you expect, that you observe when you load a single particle. And you can see here one of the really challenging and remaining difficulties, and that is that what you're reconstructing is not a scalar like bone density. It is the full stress tensor. And to make that patently clear, you have the same load being applied, but in different directions, and the photoelastic response is entirely different, depending on the direction in which you load. Right, so Wei built this prototype of loading stage tomogram. So this is a loading cell that is capable of axial loads as well as shear loads. And at the same time, rotate the sample and image the photoelastic response. So what you can see here is an illustration of the capabilities of this tomographic setup. You apply some rotary shear stress. Because of friction between the grains, you develop force chains, and what you're imaging, what this tomographic setup is imaging, is not the beads, it's imaging the three-dimensional force chains between the beads. So this is the first illustration of the formation of helical force chains in 3 dimensions as a result of rotary shear. So I will stop here just by saying that I find this development very, intriguing and very exciting. I think it provides grounds to discover really new phenomenology in this interaction between fluid and granular media, and you have direct access to that microscopic field, the effective stress. So lots and lots of things to be figured out by experimentalists and theoreticians, including a working version of tensor tomography, which does not really exist yet. So with that, I will finish thanking several generations of students and postdocs and great colleagues, and of course, sponsors who made this possible. So I'll take questions if there's time and if there are any. Thank you.